Right, in this first example of applying the slope deflection method, we've got a two-span beam. We're going to find the reactions, the shear, and the moment diagram, and the qualitative deflected shape. We've already set up the system by calling the left reaction A, the middle support B, and the right support C. We have constant EI within the span, so we can model this as two different members. Member 1 is to the left, member 2 is at the right. Member 1 has, or member AB, has twice the flexural stiffness as the right hand one, and you'll see how that comes up in a moment. Fixed end at A, fixed end at C, but a roller support at B, and that means that when we look at the kinematic degrees of freedom here, we have 0 chord rotations, we have no sway of the members, no support movements or rotations. We have theta A is 0, theta C is 0, we just don't know what theta B is. Right, now we might guess that it's going to rotate in a counterclockwise fashion. In another video we talked about the informed guess as to many of these items that we're asking for. Right, so from here we're going to just programmatically step through all the procedure for applying a first order model, that is the slope deflection method, to finding these various quantities. Right. First step, identify the kinematic degrees of freedom. We've already done that. Second step, write the slope deflection equation for each and every member n. We have 1, 2, 3, 4 member n's, so we'll have 4 equations to write. And what's going to happen is the n and the f will take on different roles, whether we're at the A end of member AB, at the B end of member AB, or at the B end of member BC, or at the C end of member BC. Right? And it just goes on in that kind of fashion. The more members you have, the more times you get to write all those. Oh, hey, for every member, there's 2 ends. So therefore, however many members we have, 2 times that, that's how many times you get to write this wonderful, beautiful equation. Woo! Alright, so note, the K for the member AB is just the I over L of the member. And in this case, though, notice that that is 2I over L. They have the same lengths between the two. The other one is just I over L, same L. So let's set then the symbol K to represent I over L, and that means that KAB will be equal to 2K. That's the simple way of getting a lot of this in here. Now the fixed end moments, we go and we look up in tables, and so note here that we have, in any structural analysis textbook, you'll usually find a table of fixed end moments. We want the one that's associated with us. We got to distribute a load across the entire member. Notice a WL squared over 12 clockwise on one end, WL squared over 12 counterclockwise on the other. But one of the things that sometimes people get confused about is they say, well, I see the fixed end to the left, but I don't have a fixed end at the right. That's okay. Temporarily, remember that fixed end is just an interpretation of the physical meaning of the term in the equation. Right? You could think that in some ways we're going to temporarily lock down everything, and then we're going to put the loads on, and then we're going to release things and allow them to do what they want to do. And when we're locking everything down, then it truly is a fixed end. And so remember, we had counterclockwise moment for the fixed end moment at the left, and that meant that counterclockwise is in the opposite direction of positive, so that's minus WL squared over 12 for that one, and it's a positive WL squared over 12 for the other one. If you're not sure where that came from, again, just hit pause on and rewind and go back on the video and you'll see it, or look it up again in your table. There's no applied loads in member BC, so those two are going to be 0. And from here on out now, it is just an application of the slope deflection equation. We have all the terms set up. Remember, here are the kinematic degrees of freedom that are either 0 or we don't know, and that's going to be key. We'll go ahead and write out the first one in all its full glory, and then we'll simplify and see how we can write these a little bit more quickly. Right? So the first time through here, we're going to start at the A end of member AB, so that means A takes on the role of N and B takes on the role of F. And from there you just substitute into all these little things just like a computer program would. So the first one here would be 4ek of member AB, which is 2k itself, times then theta A. Well, we actually know theta A is 0, so we could have just not included that term, but well, again, first time through, we'll include everything. Then change the constant. We have 2e times 2k. Got to get in the right member stiffness. That's a common mistake to make, is not to do that right. Times theta b, because we're at the far end now. And then minus 6e times 2k times the psi of that member, which is also 0. And then plus the fixed end moment, AB, has to, the order matters here on the subscripts. That's minus WL squared over 12. Right? And that clearly is going to simplify down into a much simpler looking equation. MBA now, the roles of N and F are reversed. We would have then 4ek theta near, so that's 4e times 2k of theta near, which is now b, right? And then we'd have sorry, that would pointing to the wrong one. There's your 4ek theta b. Then the second one is 2ek theta a. That's now the far end because we've gone to the other end, right? So again, swapping the roles of the N and F the letters have. And so, wait a minute, but theta A is 0, so we don't have to include that. Chord rotation term, 0. Fixed end moment for BA is plus WL squared over 12. That's it for that one. And then for MBC, it becomes even simpler here because MBC is going to have, well, we're at the B end of BC, so that's the near end, so we'll have 4E times, well, just K and times theta B. We have no chord rotation term, far end term is 0, and we have no fixed end moment. That's it. And MCB then is going to become 2ek theta B as we swap roles of the near and far end. And those are the basic writing the slope deflection equation for each and every term. Notice the member end moments are now in terms of the unknown and a loading term. And that will become powerful here in just a moment in the next step.